Well, we leave behind the world of purely 1D kinematics now and move into a world of 2D kinematics. So here we have both x and y. We're launching the Great Pumpkin through the air, and we wish to be able to calculate certain quantities of interest about its trajectory. So first of all, you'll notice we're plotting things on x versus y, and this orange curve represents where it is at every moment in time. So let's say at a particular moment, the Great Pumpkin is right here, and we can describe the vector pointing from the origin to its position as the vector r of t. Now, we can always describe this in terms of components if we define some kind of coordinate system. If we remember that we've got our I hat vector this way and our j hat vector this way. And so what we can actually do at all times is we can break this up into an x component, its x position as a function of time, and its y position as a function of time. And we can remind ourselves then that we can write this, this equation here as r of t equals x of t I hat plus y of t j hat. And this might not seem that big a deal, and we're actually rarely going to write it this way in class. But the most important thing about this whole thing, the reason we write it this way, is that this gives us the most important thing we're going to do in 2D kinematics, which is we're going to treat x and y separately. We can actually do separate. We can actually do x and y separately. We can take all of our x stuff and all of our y stuff, and they never mix. The only thing that mixes back and forth between the two of them is time. And in fact, this extends to our other quantities. If we look for our velocity vector as a function of time, well, it's going to be the derivative of our position vector. And that's actually just going to turn out to be, x prime I hat plus y prime j hat. That is to say, we have an x velocity at all times and a y velocity at all times. And again, they don't mix. And similarly, we can write our acceleration vector as just x acceleration and y acceleration. So again, I'm driving home the point here that x and y can be treated totally distinctly and totally separately for most purposes. Now, often we have a particular case where something is flying through the air under the influence of gravity as its only force. And when gravity is the only force that's applying, we have a special name for this. We call this projectile motion. And we do a ton of it. So this is, throwing a ball, launching a cannonball, any kind of thing like that. Whenever we're doing this kind of thing, it's really important to realize that the only acceleration we have in the whole system is gravity, negative g times j hat, pointing down. That gravity only acts in the y direction, never, ever, 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 ever in the x direction. And when you're solving projectile motion problems, what I'm going to recommend you do is treat x and y separately. So even make a table. Treat x and all the I hat stuff and y, all the j hat stuff, separately, right? So let's say we start off at some initial velocity, right? We have an initial velocity of v0 at some angle theta. Well, your x velocity is going to be, v0 cosine theta. And v0y will be v0 sine theta. The most important thing with projectile motion is that we always remember that our acceleration in the y direction is negative g, and that our acceleration in the x direction is typically 0. And that's, again, really super crazy important, these two accelerations. I can't tell you how many times I've seen people put acceleration of gravity in the x direction. We might start out at some initial y position, h, so we might have, y0 of h. We might have some x distance we're interested in. But the idea then is, then you do your kinematics equations, right? You've got your 3 kinematics equations, and you do them in one direction at a time. So you say, I'm going to find something in x. So you darn well better write all of your kinematics equations only with x quantities. Or if you're doing it in y, only with y quantities. The only quantity that goes back and forth is time. The only quantity that goes back and forth is time. So you got to be really sure that you do that carefully. And we'll see an example right now. Let's take as a simple worked example our turtle Spooky being launched through the air at an initial velocity of v0 at some angle of theta relative to the horizontal. And then we'll move through the air only through under the influence of gravity. I want to note here that Spooky is being launched from the ground, so the initial y position and x position are both 0, being launched from the origin. The first thing we need to do before we do any math is let's figure out what we already know. So in this case, we know our initial positions, our initial x0 and our y0 are both 0. We know that our initial velocities in the x is going to be v0 cosine theta. v0y will be v0 sine theta. Great. We know our accelerations, that our acceleration in the x direction is nothing, and our acceleration in the y direction is negative g. And then we can say, well, what do we want to know? Let's say we wanted to know how high is, let's call this y max. How high is Spooky going to get? And then conversely, let's call this distance d. How far is Spooky going to go before she hits the ground? All right. So there's a number of ways to do this, but let's talk about that first question about how high Spooky gets before reaching the apex. Like, what is the altitude of this apex? Well, we've got some different options for finding that. We could use equation 3. We could use our third kinematics equation. Remembering that something very important happens at the apex. And the thing that's very important that happens at the apex is that our velocity is purely horizontal. It is purely in the x direction. We are not going up, we are not going down. We are temporarily flat. That is, our Vy equals 0 at the apex. It's really important for projectile motion. So we could use equation 3. And that, remember, that's our V final squared equals V initial squared plus 2 times A times our displacement. Now in this case, I'm going to write it entirely in the y direction. Why am I using the y direction? Well, I'm interested in the distance in the y direction, so I better use the y direction. Notice here my final velocity is going to be 0 because I'm looking for that apex point, and I'm only using y quantities. It does still have some x velocity, but we're only using y quantities because this is a y quantity equation. And we never cross the stream. As v0 is going to be, this is again in the y direction, v0y would be v0 sine theta, the quantity squared, minus 2g. Well, my delta y, I start at 0, so this is going to be 2g y max. And so I can do a little algebra and arrive at my equation that the maximum height here, if I'm being launched from the ground, is going to be v0 squared sine squared theta all over 2g. And then I could plug in numbers if I wanted and calculate that. I could also use equations 1 and 2. I could use equation 1 to find the time to the apex, and that's actually not a bad thing to do anyway, by saying, well, my final velocity is 0. My initial velocity is v0 sine theta minus g times the time to the apex. And I could use this to find that the time to the apex is going to be v0 sine theta divided by g. And then I could plug that into equation 2, and lo and behold, I would get the exact same thing, v0 squared sine squared theta over 2g. All right. What if we then want to find our total distance in x? Well, we're going to run into a little bit of a challenge because in the x direction we have no acceleration, which means we can't really use equation 1 because all equation 1 in the x direction is going to tell us is that my final x velocity equals my initial x velocity plus, well, a times t plus nothing, which tells me that my x velocity is constant, which is also an important thing to know. In typical projectile motion, your x velocity never changes. Similarly, my third equation which doesn't have a time in it but does have an acceleration, is just going to tell me the same thing. And you can convince yourself of that. So we actually have to use the second equation, x final, which is I guess going to be d. So let me write this as d equals x0 plus v0 x t plus 1/2 t squared. Now notice, because our acceleration in the x direction is nothing, this third term actually goes away. And what we end up with, if again we start at 0, is just that d equals x velocity, initial x velocity, times the total time. Which is to say, it's just speed times time. Distance is speed times time. Now in this case, what is our total time? Well, because Spooky is being launched from the ground and hits the ground, Spooky's trajectory is nice and symmetrical. And so in fact, in this case, we can assume that the total time is just twice the time to the apex. Now, this is only true when your situation is totally, perfectly, completely symmetrical, that the time up is the same as the time down. I hope I convince you that if I were to launch you off of, an enormous cliff, that the time spent going up would be much smaller than the time spent going down. So in that case, you actually have to, if you want the total time, you actually have to split it. You got to find the time up and the time down. You got to find the total time in a different way. We'll do some of that in class. So in this case, because it's nice and symmetrical, we can take the shortcut of doubling our time to the apex. So what we end up with is v0 cosine theta times 2v0 sine theta all over g, or 2v0 squared sine theta cosine theta all over g. Now, if you are into trigonometric identities, as I am sometimes, you might instead write this as v0 squared sine of 2 theta all over g. I just want to note that if you take sine of 2 theta and you ask where is sine of 2 theta maximum, well, at 0 degrees, sine of 0 is 0. At 90 degrees, sine of, 2 times 90 is 180. Sine of 180 is also 0. So this is a max at 45 degrees, which means typically, if you are launching from ground level and hitting and coming back to ground level, 45 degrees is the optimum angle to launch things from. That is not true if you're launching off a cliff, though, and we can talk about that in class.